Tackless. Okay, so we're going to talk about electromotive force and something called Faraday's law. So I'll start out, I want to talk about this idea called an electromotive force. Let's say we have a simple circuit. Just make it as simple as possible. Where we have a battery and a resistor. And think of a current flowing like from the positive terminal of the battery, around to the negative terminal. It's losing energy in the process. Most of it in the resistor, but remember the wires have small amounts of resistance as well. And so this energy is being turned into heat. So again, we consider our current, we're looking at what we call a conventional current. Like say we have a positive charge, and it has a lot of energy near this positive terminal, and again, it's losing energy as it's going around. And then it gets to the negative terminal of the battery, and it's been losing energy this whole time, and when it goes through the battery, it's going to have higher energy. So this battery is providing energy to these positive charges. So we say this battery is a source of electromotive force. And we use this letter epsilon for electromotive force. And it's defined as the amount of energy per charge. So like if we have a charge Q going through this battery, the EMF provided by the battery is how much energy this charge gained divided by the charge itself. So if you have like twice as much charge going through the battery, it would gain twice as much energy going through that battery. So this ratio should be a constant for that particular source of EMF. Now, this would have units of joules per coulomb, which is volts. So electromotive force, it's kind of an unfortunate name because it's not a force. Forces are measured in newtons. Electromotive force is measured in volts. And battery is a very familiar source of EMF, but there's a lot of other possible sources. You could have like a solar panel, for instance. You could even use heat to produce an EMF. Or not heat so much, but like a temperature difference to produce EMF. But electromotive force, we often use it interchangeably with just like volts. But they're defined a little differently, but it's measured in volts. So you can say like a battery is 10 volts or 10 seat with a value of 10 EMF, with an EMF of 10 volts. You kind of just use them interchangeably. Okay. And like the ultimate source of it, if you look at a battery, this is a chemical reaction that's going on. For like a solar panel, you can take energy from the photons and give that to the charges that move through this potential difference. But EMF, something, just think of it as volts. Okay, so we use this letter epsilon for EMF, which is measured in volts. Okay, so let's talk about Faraday's law. This was named after a guy named Michael Faraday, who was a very unusual scientist. He was one of the greatest scientists of all times, and reportedly he was horrible at math. Shouldn't necessarily say that, but he had no mathematical training. They say he was actually a great mathematician, he just had no training at all. So he couldn't look at equations and make sense of them, but he had a very strong intuition about mathematical concepts. But yeah, he was not like a traditionally trained scientist. This was in the 1800s, and they didn't have much, standard education back then. He just got a job working in a laboratory and quickly kind of took charge of it because he was much smarter than his boss. Overall, I mean, he was a great experimental scientist, wrote several books, and very, very important in the subject of electromagnetism. So we'll come back to him. But one of the things he's most known for, so a very important thing he discovered, this is called Faraday's law. So we talked about electric flux. We have magnetic flux as well. So let's say we have a surface with an area A, and it has a normal vector n. And say we have a magnetic field passing through this surface, and the angle between the magnetic field and the normal vector is theta. Then the magnetic flux through the surface is BA cosine theta. And again, this is for a small, like a flat surface. If we had a curved surface, we could just break it up into pieces. So like basically, it's exactly the same as electric flux, except we're using magnetic flux instead of electric flux, or magnetic fields instead of electric fields. Okay, so sometimes, you distinguish it where you have like an electric flux and a magnetic flux, but usually it's obvious which one you're talking about, so you don't really need to put these distinctions on there. Okay, so I'm just going to write down Faraday's law for now. We'll talk about it, but I'm going to start out by just writing this down. So this is Faraday's law. Actually, I'll put it on this side. Okay, I'm going to put a minus sign in front because it does belong there. But this is Faraday's law. Okay, so what Faraday's law is saying, on top you have a change in flux over time. On top you have a change in flux, on the bottom delta T. So if the magnetic flux through any surface is changing in time, you have an EMF. And that's Faraday's law, and this is one of the fundamental equations of all of electricity and magnetism. Now, I want to kind of relate this to something that we can see a little easier. But so I want to make a note about this minus sign. It does belong there, but we usually ignore it. So let me give you an example. Let's say we have a wire. Say we have a conducting wire that forms a loop. Now, if there's an EMF in this loop, think about like an EMF is like a potential difference, that'll drive a current. And we can have a current going counterclockwise, or we can have a current going clockwise. And this minus sign can tell us what direction that current's going to go if there is an EMF. But we don't actually use that minus sign. There's something else we're going to talk about called Linz's law that'll tell us the direction of the current. So if you use Faraday's law in a more theoretical way, then you need this minus sign. But we're not going to have to worry about it in this class too much. Usually we're going to use Faraday's law to find like this current, and we can figure out the direction in a different way that's a little bit easier. But, I don't even remember if I put it on the equation sheet. We don't use it. But, it does technically belong there. Okay. So, what Faraday's law is saying, let me go back to this loop. It's actually pretty, if we have a conducting loop, again, Faraday's law talks about flux through a surface, and again, we can make any surface we want. So let's say this surface here. So again, it's an imaginary surface, but the boundary of our imaginary surface is a real conducting loop. And so what Faraday's law is saying, that if you have a magnetic field in the area, there's going to be a flux through this surface defined by our conducting loop. And if that flux changes, that's going to create an EMF in this loop. And because it's conducting, that'll drive a current. So let's look at the kind of ingredients of flux. We have magnetic field, area, and this angle. And so if you change any of those things, that'll drive a current. So again, say we have a conducting loop. Or a conducting ring. And say there's a magnetic field coming through this ring. If we increase the magnetic field, we'll see a current in this ring. The ring will respond to that increasing magnetic field by creating a current. So that's one way. If this was like an actual wire, for example, not like a solid metal ring, let's say we just had a wire. And there's a magnetic field here. If we just grabbed the wire and pulled it so it turned from like a circle into an oval, the area would change and there would be a current in that wire. And another way we could do it is by rotating the, like say there's a magnetic field coming out of the board. If we take this ring and just rotate it, well, I guess if it's a circle, you know, rotating it this way won't do anything. But say like this is our ring and we rotate it this way. Like here we're getting a lot of flux through the ring. If we rotate it 90 degrees, the flux is going to be 0. Yeah, like if you change the normal vector, that'll change the angle. That's a changing flux. And this rotating example, we're going to come back to that because that's an extremely important example of Faraday's law. But yeah, anytime you change a flux, you can change the magnetic field, the area, or the orientation of your surface, you will get an EMF. And if this is in a conductor, then you'll get a current. But Faraday's law might seem a little mysterious right now, so I want to relate that to something that we can actually see with what we already know, before Faraday's law. Okay, I'm going to get rid of this. So let's say we have these conducting rails. And we put a conducting bar on this. And let's say there's a magnetic field that is into the board. Okay. So our surface is going to be this rectangle here. So it's defined by this conducting bar and these conducting rails. So I don't want to actually draw the surface, but that's our surface, and there is a flux through it. However, the EMF right now is 0. Why is it 0? Well, because the flux is constant. Like right now, the flux is just this magnetic field times the area of, this surface that we defined. However, what if we move the bar? Let's say we grab the bar and we pull it to the right with a certain velocity v. So if we look at some later time, here, let's say, this is at t equals 0, the bar is here, and then at some time delta t later, the bar is over there. And so our initial surface was just like this, but as we move it, our surface is growing. And so the flux is increasing So there is a changing flux, which is creating an EMF. So if you were to do this, if you have this bar, which is free to move, so you can just slide it along these conducting rails, if you were to pull it along that, you would get an electric current. Now, you might think, well, yeah, what about inertia? What if we just push this thing and just let it go? If we could reduce friction, it would just keep moving and keep producing a current. Well, it doesn't work that way. What happens is there's also going to be a force on this bar that opposes this motion. But, yeah, let's talk about that later. So first off, what happens, we want to kind of explain this with what we already know. So what happens if we grab this bar and just pull it? Well, this is a conductor. It has electrons that are free to move. And so let's just look at a particular electron. Okay, what's going to happen if we pull this bar to the right? Now, the electron is now moving in the presence of a magnetic field. And so there's going to be a magnetic force on this electron. Because it's an electron, you know, kind of flip it around sometime. I'm going to use my left hand for an electron. So the magnetic field is into the board. So, you know, put your fingers in direction of velocity, curl towards the magnetic field. And because I'm using my left hand, that'll give a force on an electron. So this electron is, there's going to be a magnetic force pushing this electron. Sorry, that should be a negative charge moving to the bottom of the this conducting bar. And overall the bar is neutral, so there's going to be positive, like we're going to have a flow of electrons downwards that's going to create this charge separation. And because this is, it's resting on, like say this conducting rail wasn't there, if you just have this bar in the presence of a magnetic field and just pull it, that's going to cause this charge separation. However, this conducting bar is going to allow a current to flow. If you have like a positive charge here and a negative charge here, that's going to cause this, this current to flow. And so we can explain, this is called an induced current. So Faraday's law can explain this, but we can also explain it with something that is familiar to us. We know that exerting forces on charges causes them to move. And so, yeah, we want to say a little bit more about this. Now, the question is, initially this bar was, you know, just, there was no charge separation. So we pull this bar with a velocity v, and that's going to exert a force on these, a magnetic force on the charges. So again, this magnetic force is downwards. And the magnetic force, I'll write down the basic equation. Magnetic force is QVB sine of theta. And theta in this case, that's the angle between the velocity and the magnetic field. That's 90 degrees. So the magnetic force is EVB. And this magnetic force, we assume that we're going to pull this bar with a velocity v. So this magnetic force is constant. However, once we get this charge separation here, there's going to be an electric force. There's going to be an electric field. And the electric force on this electron is going to be upwards. Remember, the force on a charge, for an electric charge, F is just the charge times the electric field. And we know electric fields go from positive to negative. And the electric force on a negative charge is opposite the direction of the electric field. So if the electric field is down, the electric force is going to be up. So this force here is constant. And this one here depends on the charge separation. So as we get more positive charges building up on this end and negative charges on this end, we have a greater charge separation. The electric force is going to increase. So initially there was no charge separation. So we've got a magnetic field which is driving these charges to move. And that'll build up a charge. And as long as there's an unbalance here, the charge separation will continue to increase until this result is achieved. So, yeah, it's going to just happen automatically. Once we achieve this result, then, the force on these charges is 0, and they're going to stop building up a charge separation. Doesn't mean the charges aren't going to be moving anymore. We're still going to get a current flowing through here because of the charge separation itself. But we're going to have an EMF between these two ends that's going to be driving this current. Okay, and let me write down another equation. Here, let's go with this one. So remember this equation, E is equal to approximately equal to delta V over delta X, or it's exactly equal to delta V over delta X if we have a constant electric field. And so let's say the separation between, that separation there, let's call that L. So in this case, we can say the potential difference between these two ends, we're going to call that the EMF. Our potential is measured in volts. That would be the electric field times L. So the EMF is the electric field times the length of that bar. And now let's say we have this condition that E is equal to V times B. So, let's just to be clear, QE is, let's call that, Q is just the elementary charge, since we're looking at an electron. So EE equals EVB. Okay. So we can, we want to relate this to Faraday's law. But, just looking at this condition where, this charge is going to continue to build up until it reaches this potential difference between them. And, we want to show that Faraday's law will give us the answer that, that we expect from what we could do previously. But Faraday's law works in cases that are very difficult to analyze in terms of like forces on moving charges. So going in the future, we're just going to go with Faraday's law, but I want to at least show that we can duplicate the results for one case. Okay, so what do we get for the EMF? From this case, we have E times L, where E is equal to V times B. So we have V, B, L. So that's the EMF that we get, and that's a good form to leave it. So let's write this here. It's actually a good form to leave it in because, these are fixed for this problem. Like we're imagining a situation where we grab this bar and we pull it with a velocity v. So we just pull it. The magnetic field is fixed and L is fixed. We're not going to change the geometry here. And so this is a perfectly fine way to express the EMF. Just from looking at forces and charge separation. this is what we would get. But now let's look at what Faraday's law has to say about this. Let's calculate the EMF using Faraday's law. So again, we're just looking at the magnitude of the EMF. I don't care about that minus sign. Now, what is the flux in this case? Remember, our flux is, or the area is this surface here, defined by these rails and this conducting bar. So let's say the distance from the end of the bar, or from the end of the, from this end of the rails to the bar, let's call that distance x. So our flux is the magnetic field times the area. So we have B times the area is just L times X. So yeah, in this case, we have a constant magnetic field, and it's perpendicular, so we don't have to worry about that angle. So a flux is just the magnetic field times the area. So the area of this rectangle would just be L times X. Okay, now B and L are constant. So I'm going to go through this the long way. We have delta. That's like the final value minus the initial value. So we'd have BLX final minus BLX initial. And because B and L are constant, we can factor that out. Okay, so we take the BL out. And then what we have is X final minus X initial divided by delta T. Now, X final, that would just be this position here minus the initial. X final minus X initial is just delta X. So what we're getting is our EMF is BL delta X over delta T. And delta X over delta T, that's just the velocity of this bar. So we're getting the same result using Faraday's law that we got from looking at like magnetic forces. And how this charge continues to build up until we reach this condition here. And so Faraday's law is kind of a nicer way of doing this. But just like trying to analyze something like this in, if you take another example, let's say we have a loop in a magnetic field. And say we rotate this loop. So we take it and we rotate it. That's going to drive a current in this loop. Try explaining that with looking at forces on moving charges. It can be done, but it's very difficult to do. So Faraday's law is very nice. I guess in a sense you could say it's nothing new. But it actually goes beyond what we've done before, because this is considered a fundamental law of the universe, of the subject of electromagnetism, where we can even go beyond these like physical examples where we have charged particles. So you could even do this, like say that this was out in space. There's no matter around. There's a magnetic field coming from matter somewhere else. We have a region of space where there's just no matter at all. And we can imagine some surface, and if we rotate that imaginary surface, there's going to be an EMF. And it won't drive a current because there's no charges, but that EMF still does exist. And so, Faraday's law does actually go beyond what we've been doing before. It is a fundamental law. It is something new. It's just a little bit harder to see what's new about it. So in this class, mainly we focus on just looking at it as something we can use for convenience. Because solving a problem like this, what happens if we spin this loop? What kind of current are we going to get out of that? That'd be very difficult to explain by looking at the forces on the moving charges. But on a more fundamental level, this can be used even in the absence of matter. And one case that is important is radiation. We're going to come to radiation later. But yeah, radiation consists of changing electric and magnetic fields. And Faraday's law can be used to explain that, even in the absence of matter. So yeah, this is a very fundamental law. Mostly we use it in this class to do things that we can in theory do otherwise. So we're kind of looking at it as more of a convenience, but yeah, very important. So that is called Faraday's law. And I want to talk a little bit about that minus sign again. Again, we're not going to really use it, so I'm not going to bother with it. Now let's go back to this example. And again, we can see from the charge separation, the current is going to go counterclockwise. So let's just remember this problem. Clockwise, the current is counterclockwise. And just because this picture is cluttered up, I'm going to fix it up. I'm going to redraw it. So remember we had a magnetic field into the board. And we're taking this bar and pulling it to the right. Okay. So we already saw how we can get the EMF using Faraday's law. It was actually much simpler than doing it by looking at forces on charges. But if there's an EMF, that's going to drive a current because everything is a conductor here. So the question is, what direction is the current going to go? And again, we could just use it, Faraday's law, with that minus sign. But usually it's much nicer to use something called Lenz's law. So Linz is one who came up with that. And let me actually read. I think I wrote down kind of a precise, no, I don't even know if I wrote down. But the idea of Lenz's law is, yeah, let's forget about this problem for a moment. Let's say we have a ring. And say we just create a current in this ring, that's going to create a magnetic field. Where if you look at, here, it's going to create a field that's coming out of the board. Inside the ring, the magnetic field is coming out of the board. Right hand rule, curl your fingers in the direction of the current, thumb points out of the board. So if we create a current, that's going to create a flux through this this ring that we created. So it's going to be like a wire. And that current is going to create a flux. And so Faraday's law, we have a changing flux creates a current called an induced current. And that induced current is going to affect the flux. Like say we have a current in some random direction. Let's just say there was a current going clockwise. That would create a flux into the board in this region, on our surface here, defined as before with these rails and this conducting rod. So the current creates a flux in our surface as well. And so, using Faraday's law, we see we get a current, a changing flux creates a current, and that current is going to affect the flux itself. And so what Lenz's law is saying is that the induced current is going to oppose the change in flux. So let's apply Lenz's law to this. Now, it might sound simple, and I guess in a way it is simple, but it's something that takes a lot of getting used to. Just like the right-hand rule. So this is one of those things, every class from now until exam 3, we're going to practice the right-hand rule and Lenz's law. I found that's necessary because it's like we're talking about a current here. The answer is either clockwise or counterclockwise. You can flip a coin and get it right half the time. And the first time I taught this, the students seemed to understand it. But, when it came to the exam, it was like flipping coins. There was no real understanding, at least across the entire class. Individual students might have. But really, I mean, it was one of these subjects where I've learned that the only way to really get Lenz's law is just, we'll spend a few minutes at the beginning of every class just practicing it. And then by the end, that turns out to be very successful. So anyways, we're going to apply this using Lenz's law. So remember, the induced current is going to oppose a change in the flux. So what's happening here, what's causing the current is we're moving this bar. And what that's going to do is the flux is increasing into the board. So let's say we move this bar. Like right now, the flux into the board, because magnetic field's going in, would just be the magnetic field times this area. So if we move this bar over, we have a constant magnetic field. It's the same strength, except now there's a bigger area. So the flux increases into the board. So that means the induced current, so the change is into the board, so the induced current will create a flux out of the board. So the easiest way to do this is just, point your thumb out of the board, your fingers curl in the direction of the current. And so we get a counterclockwise current from using Lenz's law. So that's what we got the first time by looking at the forces on these moving charges. And now we get the same thing using Faraday's law and Lenz's law. So again, it might seem simple, but there's a few steps involved. And it's something that just requires a lot of practice. But we did get the same result. Now I want to talk a little bit more about Lenz's law. Like, why is this the case? Or what does it kind of mean? So let's look at a simple circuit. I'm going to throw a switch on here. Okay, so we have a battery, a resistor, and now there's a switch which can go in two positions. We can flip the switch towards A or towards B, and let's say we can flip the switch instantaneously. Not exactly realistic. Let's say we can do it fairly quickly. So what happens, we flip the switch towards A, and we have a current, which is going from the positive terminal to the negative. And so again, curl your fingers in the direction of the current. That creates a magnetic field into the board. Now what happens if we flip the switch to B, like instantaneously? So again, not the most realistic thing. Let's say we instantly flip the switch to B. Now what's going to happen to the current? There's nothing powering it anymore. It's not connected to the battery. I mean, you might think it's connected over here, but that's not going to do anything if, you need a continuous loop. It'd be like like say you have a flashlight and you touch one terminal of the battery with a flashlight, nothing's going to happen. So this has absolutely no effect. We might as well erase it. And we know the result: if we remove the battery, the current's going to disappear. However, it cannot happen instantaneously. And, that's obvious if you think about it, because this current consists of moving charges, and they can't just stop instantly. So we know there has to be some delay, but Faraday's law can explain this as well. So right now, what we have is a flux into the board. Okay, and then we flip the switch, and the current is going to go to 0. So ultimately, the ending flux is going to be 0, so there's a changing flux. And this changing flux is going to create an EMF that can drive the current. So what direction is that going to be? And the flux starts out into the board, but it's going to go to 0. So the change in flux is out of the board. So our flux initially is into the board, but it's going to end up 0, so the change is out. Look at it from a different perspective. Let's say like this is into the board. This is out of the board. So it's like we have an initial flux of 0, or into the board, but it's going to end up 0. So the change in flux, it's going from here to here. So the change in flux is going in the direction out of the board. And so the induced current is going to create a flux into the board. So put your thumb into the board. That means that the induced current is going to be clockwise, which is in the same direction as the initial current created by the battery. So if you remove the source of voltage, then the battery isn't powering this anymore, and so the field is the current is going to start dropping, but that changing current is going to create an induced current in the same direction. And so it's going to the current can't just, if the current just instantly disappeared, that would be a huge change in flux. Remember, change in flux over time. If it disappeared, like in a nanosecond or something, if it just almost instantly disappeared, this would be a huge EMF that's driving the current in the same direction that it was already going. So the more rapidly you try to kill off that current, the greater Faraday's law is going to keep on making that current, keep driving that current. And so the point is, it's not going to just drop, the current won't just drop instantly to 0. Now, going into more detail, like how exactly is the current going to drop to 0? We know it's going to start out and it's going to end up at 0, but it's going to drop, and kind of explaining the details, we don't bother with that. That requires calculus, and in a problem like this, it wouldn't even be interesting anyways. But we'll talk a little bit about the things that would affect that. And it's mostly geometry, like the size of this loop and things like that. Basically, we could give a number to that, and we are going to, but we're not going to go into too much detail. But we call this inductance. So like this circuit has a certain amount of inductance that will continue to drive this current. But for a circuit like this, it would not really be a significant amount. So we could usually just ignore it for a circuit like this. Now there is a device that would add a lot of inductance to a circuit and could have a huge effect on it, and that device is a solenoid. And again, that might not be too surprising. So remember, we drive a current through this solenoid. Remember, it creates a magnetic field through like the whole length of the solenoid. And so there's a lot of flux through this solenoid because the angle, the magnetic field, if you look at each loop of the solenoid, normal vector and the magnetic field are parallel to each other. So like there's a large flux through each coil of the solenoid, and there's hundreds of coils. So like the flux through this solenoid is enormous, and if you try to change it, you could get a very significant result. So technically, and again, we are going to talk about the inductance of a solenoid later, but theoretically, you could find the inductance of a circuit like this, but it's usually too small that we wouldn't know or care about it. So it's something you kind of have to build into the circuit if you want it. But yeah, we definitely did not cover this topic very thoroughly because it takes a lot of practice. But again, we'll be doing that every day until the exam. So I think that'll be it for this lecture. And yeah, see, next we are going to talk about inductance. But yeah, the problem, like say we put a solenoid in this circuit, we're not going to really go into details about those kind of circuits because it brings us right into calculus and there's no way around it. So we'll talk about inductance, but not get into too many details. But that'll be the next topic.